okay? But when I deal with the students and I talk about superheroes and their powers, I tend to come up with 3 different questions. So I talk about, is the power we're talking about even possible? And this is really that fundamental science question. Does it violate something we know is fundamentally true about the universe and we never ever expect to be violated? Okay? If we want to assume it doesn't violate anything fundamental, but it looks like it's weird, maybe we ask, how could they do it? And this might get more into technology. You know, or is there some cutting-edge technology that might allow them to do this? Invisibility is a fun one for that, as people start messing with properties of matter to bend light in interesting ways and perhaps get some form of invisibility. And the third question that kind of combines all of these is, even if you have a superhero with superpowers, they still have to interact with the world. And the great example of that is, suppose I'm Superman or Flash and I want to run really fast. I might have super strong legs, I might grant you that, but there's only so much friction between my foot and the ground. You know, if I take the fastest person in the world and try and race them on ice, I figure I've got a good chance. Okay? I'm probably not going to beat them on the ground, but if they get us both on ice, we're limited by the friction between us and ice, and the fact that they're stronger and faster is less important. Okay? And so that gets into that area of how do you interact with the rest of the world. So these are the questions I tend to look at. Now, I've picked 3 super events or superpowers to look at. I've taken a couple of video clips. These video clips have taken an interesting route. It allows me to like self-promote here. So this is from the first Superman movie, which I don't have a copy of, but I have a copy of the National Geographic special I was in talking about the Superman movies. And so I was able to steal the clip from that. Okay? So I'm going to show the clip. So this is in the first Superman movie. You may remember he at one point tries to turn time backwards. So there's no sound, but Lois Lane just got killed. Superman's sad, and he starts flying around the Earth very, very fast. Okay? And what he manages to do is stop the Earth spinning, okay, and then spin it backwards. And as we all know, this will turn time backwards. Okay? And this is a great one because what I love about it is, and there's time going backwards, all the rocks are going up the hill, okay? What I love about it is first of all, there's this clear fundamental issue. If we spin the Earth backwards, time doesn't go backwards. We just all get hurt, okay? Bad things happen, okay? But then you can ask students the question, can you go back in time? And they get very nervous suddenly. They don't know if this is a trick question or not. And what's fascinating to me is when you start thinking about relativity and general relativity and the nature of space and time, and you ask yourself, okay, time is just another dimension that's very similar to space, slight differences, you can start talking about things in physics called closed time-like curves, where you actually can make a loop in time and go around and come back. Now, whether you can actually achieve that, what you really need to do that, these are open questions that you can research. So you can talk about time travel in a sense. Then you can come back to Superman's idea of trying to spin the Earth backwards. And you actually get to talk about freshman physics. Because you can ask, what does it take to stop an object that's spinning? Well, you need to apply a torque to it. And then you need to spin it the other way. How could you do that? Well, Superman's spinning in the atmosphere. Maybe there's some friction between him and the atmosphere. This generates a force on the Earth, slows it down. And you can actually do what we call in physics back-of-the-envelope calculations. This is where we take some numbers and we make a quick estimate. How fast must Superman be going to stop the Earth and spin it backwards just from the drag between him and the atmosphere? I did this calculation for students a number of years ago. I always forget the exact number because it was really big. It was like 10 to the 8th times the speed of light. Okay? So you run into another fundamental limit. We know you can't go faster than the speed of light. And so you get to come into this other issue that you get to talk about. And I like this one because it comes back to this idea of what's fundamental versus technological limits. There was a time where people would say, oh, it was impossible to go faster than the speed of sound. But that's talking more technologically. I mean, they knew you could go faster than the speed of sound. Light goes faster than the speed of sound. But there's a shock wave, and they assumed you could just never build anything that would survive that. And clearly we do now. But with light, we have a much different question. And we know it's kind of weird in science, because we say in science that you can never prove anything to be absolutely true. You can only prove things to be false. And yet we stand up here as physicists and say, you can never go faster than the speed of light, and we know it. And you can talk to students about what do we really mean by that. And when you look at this behavior, this prediction of going faster than the speed of light, it is so interweaved in every theory we do. And I love to give the example, GPS wouldn't work if this was wrong. Okay? And the particle accelerator at CERN wouldn't work. I mean, these are such different phenomena that it's very hard to imagine that this isn't a fundamental property of the universe. Does that mean we would never, ever go faster than the speed of light? Well, it depends how you define it. Maybe we'll find some trick around it, but as we understand it now, it's a fundamental law of the world. So that's a really nice one.